So Madhukar, if you can introduce the speaker formally before we start.
Okay,
Okay.
good morning, respected participants, scholars and eminent faculty. Welcome to today's FDP session. Today is 18th April 2024. We have two sessions today. First session is on very pertinent topic, Metasurface for Future Wireless Communications by Dr. P. Yogeshwari, followed by second session, an industry session by Rebecca Technologies. It is privileged to introduce Dr. P. Yogeshwari, a distinguished academician and researcher whose journey through academia has been marked by remarkable achievements and contributions to the field of electronics and communication engineering. Dr. Yogeshwari started her academic career at the prestigious Madras Institute of Technology, Anna University, where she obtained her bachelor's degree in electronics and communication engineering in 2014, laying a strong foundation for her future endeavors. Driven by her passion for advanced research, she continued her educational journey at the College of Engineering, Guindy, Anna University, where she earned both her master's degree in 2016 and doctoral degree in communication system in 2019, a distinguished achievement for her innovations significantly contributed to the academia. Currently serving as assistant professor, researcher at Shastra University, Tanjavur, since 2018. Dr. Yogeshwari has been instrumental in nurturing young minds while actively engaging in cutting-edge research. Her commitment to excellence is evidenced by her extensive publication record, comprising 18 research articles in prestigious journals such as IEEE Letters, IEEE Transactions, and various other peer-reviewed international publications. Moreover, her academic journey extends beyond publications as she holds an impressive tally of 8 Indian patents grants, a testament to her innovative spirit and problem-solving acumen. Dr. Yogeshwari's research endeavors are further supported by her involvement in two ongoing research projects funded by IIT Tirupati Navaska iHub Foundation, showcasing her ability to secure and execute significant research grants. A distinguished member of IEEE community, Dr. Yogeshwari's affiliation with the Antenna and Propagation Society underscores her expertise in her research domain. Her research interests span a wide spectrum, encompassing reconfigurable antennas, intelligent reflecting surfaces, microwave sensors, beamforming, deep neural networks, and FPGA-based SDR for SATCOM applications, reflecting her multidisciplinary approach towards solving contemporary challenges. In essence, Dr. P. Yogeshwari stands as a beacon of excellence in academia, whose relentless pursuit of knowledge and innovation continues to inspire and shape the future electronics and communication engineering. With this brief bio, I invite Dr. Yogeshwari to share her insight on Metasurface for future wireless communication. Dr. Yogeshwari, over to you.
Thank you so much for the nice words, sir. Firstly, I want to start the presentation by thanking the organizers for organizing a wonderful knowledge transfer sessions among this academic fraternity and for giving me this opportunity to present today. And I would like to start the presentation by introducing my institute, Shastra University, which was founded in 1984, and it has its significant milestones like installing this type of core building and getting this world-class manufacturing facility and setting up this TBI for 3D printing and IoT category and several other international accreditations. And it has also received MHI funded accelerated BSL3 certification. So with this, let us start. I'm starting today's presentation. So this slide just gives the outline of today's presentation, where we'll be seeing about this current and future wireless communication scenario, and what exactly is a metasurface, and why do we need this metasurface, and what are its potential application in wireless communication, and properties of metasurface, and how metasurfaces are going to help us in developing this reconfigurable intelligent surfaces, which are considered to be the viable contenders for 5G and beyond communications. So this is the outline for today's presentation. So as we all know that this sub-6 band is highly congested, we'll be moving on to this millimeter wave frequency. So during the time, with the existing facility, we are moving on to the higher frequency, means the price will increase and there will be several hardware complexity, interference issues will arise, and the end devices will consume more energy. And these are all the issues if we are moving from if we are moving to this higher frequency domain using the current technology. One viable solution is to use this reconfigurable transmitters and receivers to avoid these issues. So, and also one more issue, if you are going for this millimeter wave now, there will be severe path loss, because if the frequency is higher now, the path loss will be higher, and all those high frequency signals are atmospheric sensitive. So these issues are also to be taken care. So what happens, like we'll be having base stations at short range, and the number of radiators are going to be higher when we are going to this higher frequency range. And this is how the structure of RIS will be also. So the future wireless communication is having a great role for this reconfigurable intelligent surfaces. And in the upcoming slides, we'll be seeing how Metasurface is going to be a fundamental entity to develop this reconfigurable intelligent surfaces. So these are all mostly passive devices. If this device is being used, interference will be very less, and maintenance cost is also very less. So basically, we'll be developing a smart environment using this reconfigurable intelligence services. So this picture just shows how a reconfigurable intelligence surface is helping to transmit the signal, even if the receiver is in the blind spot of the transmitter in an indoor environment. And here we are seeing like how the research interest for reconfigurable intelligence surface getting increased drastically from 2015. And coming to this evolution of metasurface and reconfigurable intelligence surface, everything started from this diffraction grating, which is used to just split a single light beam into multiple beams. That is diffraction grating. And one more concept is this reflector array antennas. So where we will be sending this RF signal. Once the RF signals are getting impinged on this reflector array antennas, we'll be getting multiple RF signals depending upon the number of reflector array elements we are having on the panel. So next is this metasurface. So metasurface are made up of meta atoms, which are not physically present in this. We have to develop those components which have the capability to just manipulate the electromagnetic signal. So that is the capability of metasurface, and we'll be seeing what metasurface is. So using this metasurface, we can develop the reconfigurable intelligence surface. So this is the evolution. So basically, for a smart environment, we need this element by element tunability using this RIS. And here we have this multifunctional metasurface, wherein the metasurface, it's sending the signal from transmitter to various receivers, and it is also blocking the signal in undesired direction using the wave manipulation concept. So basically, we are having this electronics domain, photonics domain, and plasmonics domain. So if we are in electronics domain, the size reduction is up to 10 nanometers, and it is offering the operating speed up to 1 gigahertz. We can't go beyond 1 gigahertz due to the slight diffraction issues. But if we are in photonics, that is, we are dealing with light, the speed is very, very higher, but all the optical components are more bulkier. On the other hand, we have plasmonics, where the light will interact with nano-sized elements. So that is offering less size, and also like they are also operating at a greater speed. So this is the scenario we are in right now. So this picture is nothing but a metamaterial. This is how a metamaterial will look. Now, what exactly is a metamaterial? So if you are considering the natural material, we are having, there will be atoms. Atoms are the fundamental thing in a natural material. But in a metamaterial, we have this meta atoms. So this is how the configuration is. We have a meta atom, and if the meta atoms are constructed in a 3D fashion, that forms metamaterial. And if we are arranging this meta atom in a 2D plane, that is a metasurface. So what exactly is a meta atom? Why these things came means like if you are looking upon this periodic table, we have several elements, but if you are just clubbing one element with the another element, we are not able to get the properties whichever we want. So clubbing two elements, by clubbing two elements, we are not able to manipulate the electromagnetic wave to a far extent. So people try to construct atoms to manipulate the electromagnetic waves such that the manipulation does not depend upon the chemical constituents, but rather it depends upon the physical layout of the meta atoms. So the wave manipulation that we are going to talk about today entirely depends upon the single meta atom, how the shape is going to be, how the size is going to be, and how it is arranged as an element, like this, either a 2D element or a 3D element. Only the physical layout matters for this wave manipulation, whereas the chemical constituent is not going to play a significant role. Whether it is silver or copper or aluminium, the change is not going to be that much significant. So how should be this meta atom? Basically, this meta atom should be having a size less than, very, very less than this operating wavelength, and the interelemental spacing between the meta atoms should be less than lambda by 5. That is the scenario. We are creating a meta surface. So this is why we are going for this meta surface, to manipulate the waves without depending upon the chemical constituent. Whereas the configuration, this array arrangement and this unit cell will be a critical factor for the wave manipulation. So basically, this is how the hierarchy is. We'll be having this natural atoms. So from that, we'll be having naturally existing materials. So from that, we'll be having this meta atom or cells. So from that, we'll be having the meta materials. If you are taking only one 2D plane of this meta material, that is called meta surface. So this is how the meta surface will look like. So they are very, very tiny, because the size is very, very less than the operating wavelength. So basically, this unit cell, it can be either a split ring shape or it can be loops. So this is how the physical appearance will look like. And there are several existing designs that we'll be seeing in the future slides. This is how the orientation would be. And so before moving on, like this metamaterial is classified into 3 different types. That is this epsilon negative, mu negative, and double negative. So this second quadrant, third quadrant, and fourth quadrant are metamaterials. And in the first quadrant, we have material type called this double positive, which means all the elements that are existing naturally. So that has this permittivity and permeability. greater than 0. So we have to understand this permittivity and permeability before proceeding to the other slides. So permittivity is nothing but the ability of any material to restrict the electric flux lines that is getting formed. And this permeability is nothing but the ability of the material to create more magnetic flux lines. So higher the permeability, the more easily the element will be magnetized. So in the first quadrant, this epsilon and mu, if for any material, if this epsilon and mu is greater than 0, that is the conventional material existing in the real world. That is this double positive material. And coming to the second quadrant, we have this ENG, that is epsilon negative, where this epsilon will be less than 0 and mu will be greater than 0. Example for this is plasma wire structure. This wire structure, how it is going to look like, we'll see in the next slide. So this is this epsilon negative. Basically, this epsilon negative is an evanescent mode. Like if you can see this, we are having an air, that is, we are seeing one electromagnetic wave that is trying to enter this epsilon negative material, but it is not going inside. It is getting reflected back. So this will offer only evanescent. This will offer only evanescent. But whereas, and one more thing is we have this mu negative in fourth quadrant. Mu negative means epsilon will be greater than 0 and mu will be less than 0. Example for this category is ferrites and splittering resonators. How a splittering resonator will look like, we'll see in the next slide. And this mu negative will also not allow the electromagnetic wave to pass through. See, this ray is here and the wave is getting reflected. So this will also offer evanescent mode. So the material in quadrant 2 and quadrant 4 will offer only evanescent mode. So the transmission is not possible. But we have some interesting material in quadrant 3 that is called this left-handed materials or metamaterials. So even though all the three quadrants are called metamaterials, the more which we are using prevalently is the material in quadrant 3. So which has negative epsilon and negative mu. Epsilon less than 0 and mu less than 0. So it's called double negative. So the one more attribute we have to see here is, so we all know in Snell's law, if an electromagnetic wave is moving from one medium to another medium, there will be refraction. And the refraction depends upon the refractive index of the material. So it is getting refracted. So this is how the Snell's law. This is for double positive natural materials. But whereas in quadrant 3, we have this metamaterials, you can see how the wave is manipulated. It is just getting deviated from the Snell's law. Here we use generalized Snell's law. So this is how the wave is manipulated. That is not positive propagation vector. Here we have a negative propagation vector. In the first quadrant, we have the positive propagation vector, whereas in the third quadrant, we have the negative propagation vector. So this is the wave manipulation done by this metamaterial. So coming to this wire structure and splittering structure. So this is how the wire structure is. In quadrant 2, we have this wire structure which offers the negative permittivity. This is the wire structure. And in quadrant 4, we had the splittering resonators which offers negative permeability. We have the splittering resonators. So the capability of this wire is offering negative permittivity, and the capability of the split rings is to offer negative permeability. If you add both those things, you will be having negative permittivity and negative permeability, which we will using which we can design a metamaterial. So quadrant 1 is the natural material, anything which is existing in the real world, and quadrant 2 and quadrant 4 are offering us the evanescent mode. So in quadrant 3, we are having this wave manipulation using double negative metamaterial. So it is wise to use this double negative metamaterial. So to explain this metamaterial concept with respect to the wavelength, so let us suppose these are the atoms arranged in an element. So, and let us assume this is the shorter wavelength. The frequency is higher, which means the wavelength is very, very shorter. At this domain, the wave will be able to recognize the atoms. The resolution is higher here because the wavelength is very, very shorter. Okay, but here the wavelength is very, very larger and the resolution is very, very small. So here the wave will not be able to identify the locations of the atoms exactly. So this is, if you are assuming this d, that is distance between the two atoms as d, if the d is very, very greater than lambda, if the d is very, very greater than lambda, the wave can easily identify the atoms. But whereas if the lambda is very, very greater than t, the wave cannot see where exactly the atoms are. But in between, we have a region called this metamaterial region, where this interelemental distance d is equal to lambda by 4 or lambda by 5. So the metamaterial concept basically lies here, where the interelement distance will be lambda by 4 or lambda by 5. So this is the region where metamaterial concept will be lying. So this picture shows the wave manipulation by a metamaterial. So basically, if any electromagnetic wave or light is moving from vacuum to any conventional material, this is how the propagation will be. But whereas in metamaterial, the wave propagation is in a different way. The wave is getting manipulated. So this is the property of this metamaterial in which the wave is getting manipulated. Because this is not because the material will offer negative permeability and permeability, and the meta atoms are very, very less than the wavelength, which is wavelength of the electromagnetic wave, and also the interelemental distance between the meta atoms are equal to lambda by 4 or lambda by 5. So these properties attribute for this wave manipulation. So at this point, I want to highlight one important property of this metasurface, that is called clocking property. That is, metasurface or metamaterials are capable of hiding certain materials. Like say, for example, the inner circle. The smaller circle is the material you want to hide. This circle is the material you want to hide. We can design metamaterials of that specification such that the electromagnetic waves will bend around the object which is to be hidden. So the user, if there is any detector to detect this object, will not find this object is present here. So this way, the clocking is being done here. This is one of the important property of this metamaterials or metasurface. So to be more clear, so we have a solid object here, and in a normal scenario, there is any light getting impinged on it, we'll be seeing the solid object. But if around the solid object, if there is any metamaterial, like the structure of the metamaterial is getting zoomed, it is zoomed here. You can see the split rings. The metamaterial that is used here is the split rings. So if you are using a metamaterial, clocking will happen, and this will be hidden. This will be hidden. So this is the clocking property of the metamaterial. So this is one of the unique, one of the highlight property of this metamaterial. So this is the clocking. And one more thing is, this is the metamaterial lens and metasurface lens. Okay, so this is highlighting that metamaterial is a 3D object, and metasurface is it's a 2D plane. That's why we have a straight line from a front view. So, and the pictures at the left hand side just illustrates the clocking property of metamaterial and metasurface. So one is a 3D object and other one is a 2D plane. That is the difference. So, and also metasurface can widely be used in terahertz application also. And the potential applications of metasurface are polarization modulation, beam forming, and controlling of signals, beam focusing, and holograms. So if this is a metasurface, we all would have heard about this right-hand circular polarization and left-hand circular polarization. So this metasurface is capable of changing the polarization of electromagnetic wave. that is from right hand circular polarization to left hand circular polarization. And also there are two types of metasurfaces. One is transmissive metasurface and the other one is reflective metasurface. Transmissive metasurface means it can transmit the signal from one end to the other end, whereas the reflective metasurface means it will be reflecting back the signal towards one side itself. We seeing those things also. So basically, by modifying the electromagnetic wave, this metasurface is capable of changing the amplitude of the signal, frequency of the signal, polarization, and phase of the signal. This is the capability of metasurface. So let us assume this is a dielectric medium. So we are going to discuss now how the phase is getting manipulated in a metasurface. So if this is the dielectric medium, and let us consider this region of thickness d alone. And so whenever a wave is getting propagated inside this dielectric medium, the wave will be having phase change. Obviously, whenever a wave is moving, there will be a phase change. That phase change, so I'm representing that phase phi as phi of x comma y, because you are in xy plane. So the phase change in xy plane is equal to n of x of y, that is refractive index, into k into d, where k is the phase constant and d is the interelemental distance. So this is how the progressive phase shift will be whenever we are in a normal dielectric medium. But if we are in a metasurface, so metasurface are the surfaces we are just manufacturing. That is, these are all engineered products, engineered materials. So we can have the meta atoms in various shapes and various orientations, and each element will offer phase shift at a specific rate. So we are altering the phase. If we are in a dielectric medium, the phase will be constant. The phase won't change. Phase phi is equal to n into k into d. But whenever we are in a metasurface, the length, the orientation, the spacing of a specific element can be different, which is in our hands. So depending on that, the phase is getting altered. So if you look along the y direction, if you just observe, all the patterns will be same. So along y, you can't expect phase change. But along x, if you observe the pattern, the orientation, and this, the element are different. So this way, the phase is getting changed. And that is represented as, and that can be represented as d pi by dx. That is rate of change of phase along x direction. So this will be the fundamental thing for the wave manipulation, because the phase is getting altered, because we are altering the element's orientation. So that specific manipulation can be mathematically represented as d phi by dx. So the phase manipulation that we did here, if you are trying to do the same manipulation in optical domain, we have to use this lens and prisms, diffraction gratings, and gradient index plates, and all these entities are bulkier, but that can be easily replaced by a thin metasurface. So metasurface is not going to occupy that much space. They are very, very small. So size wise also we are getting benefited. So as we discussed before, Snell's law is getting replaced by generalized Snell's law. In Snell's law, we know that this that is, if there is any incident wave, there is any incident wave that will be reflected, and also it will be get refracted. That is the thing in Snell's law. That is, but here in this, if we are assuming any metasurface, the Snell's law is not valid. We move on to this generalized Snell's law. So this is the incident beam. We'll be having reflection this way. So that reflection is called anomalous reflection. And refraction is going to be the other way, not as the regular refraction. That is called anomalous refraction. So we all know that this in an ordinary Snell's law equation, we know sine theta r by sine theta I is equal to n1 by n2. That is the ratio we know. But here, um, in the generalized Snell's law, we have n1 sine theta r minus n1 sine theta 1 is equal to 1 by k naught d by dx phi of x. So this k naught is nothing but the propagation constant, which is representing the wave propagation. And this d phi of x by dx is nothing but the phase change we talked about here. Because of this phase change only, we're having this additional term, and this is the additional add-on to this generalized Snell's law when compared to the regular Snell's law. So this is the wave manipulation, and these are all the different structures that are existing in literatures, like coffee bean structure, patch with slot, and several other structures. And also, if you observe, more specifically in F, we have this orientation in different ways. So these all will counter for the wave manipulation and phase change. The orientation is completely different. So these are all the examples of existing designs in literature. So now from this slide on, there will be several use cases where this Metasurface is getting used in a practical wireless communication scenario. So firstly, there is a prototype of this fabricated Metasurface. So here the Metasurface they are trying to design is an intelligent Metasurface. Why we are calling it as intelligent Metasurface? Because if you see here, we are not having any active elements here like pin diode or varactor. Nothing is present here. But if you observe here, in between the meta atoms, there are several small tiny entities. They are nothing but pin diodes. So those pin diodes can be turned on or turned off, which will alter the electrical, which will, if it is turned on, that particular element will be connected. If it is turned off, the particular element will be disconnected. So depending upon that, the wave manipulation will be done. That is why we have this pin diodes here. So whenever there is a pin diode, there should be a biasing circuit also to bias the pin diode. So that's why you will be having we are having this DC bias network, DC network, and to excite this this entire element, all the elements, we will be having RF input. Then to just to decouple this RF input and this DC input, we have to develop a decoupling circuit. So that is explained here. So whenever we are planning to design this intelligent Metasurface, we'll be using this pin diodes or actuators. So during that time, we have to focus on designing this decoupling structure also. So this is how the prototype of an intelligent Metasurface would be. So next one is here, along with the Metasurface, we are having FPGA board to make this Metasurface a programmable one. So basically what we'll do, like if there are n columns in a Metasurface, if there are n columns in a Metasurface, we'll be having n digital bits. We'll be having the digital data. So that should be grouped into n bits, and each bit will be assigned to the one particular column of the Metasurface. So it is 0, 1, 0, 1, 0, 1 here. It can be anything. So that is how the things are done here. If it is 0, these elements will be the diodes along this column will be disconnected. If it is 1, the diode along this column will be turned on, and this continues. So depending upon the on and off state of the pin diode, we'll be having several beams. So these are the different possible beams. We have this 16 beams depending upon this bit states. 0, 0, 0, 0, 0 means the pin diodes will be off, and just we are having a simple Metasurface because all the pin diodes are in off state. And if it is 0, 0, 0, 0, 1 means the last column will alone be turned on. So like that, we have several combinations. So for each combination, the beams would be different. So, so this is how the programmable metasurface is going to be. And to be more clear, what happens if this pulse waveform, if it is 0, 1, 0, 1, if it is 0, the pin diode will be off. So no current flow will be there. If it is 1, the pin diode will be on, and then the current flow will be there from one meta atom to the other meta atom. So this is how the wave manipulation is done using an metasurface that is connected with the FPGA board. So this is a programmable FPGA. And then here we have this application of metasurface where it can, like we talked in the few slides before, we talked about the fact that a metasurface is capable of converting the frequencies, changing the polarization and amplitude also, right? So if see, we have a metasurface here, but from that metasurface, there is a RIS that is getting developed. That is, this entity is nothing but, in a micro base station, there is a RIS which is having this metasurface. So from here, we have a different frequencies. This element is capable of transmitting and receiving different frequencies because of the wave manipulation. So lower frequency is sent to this small cell base stations, and middle station is sent here, and middle frequency is sent here, and high frequency is sent to some mobile users. Apart from this, same frequency can also be transmitted between two RIS, and frequency conversion, that is changing from one frequency to another frequency, is possible using this wave manipulation technique. So that's why from lower frequency, there is an up conversion that is getting connected to this satellite, because if you want to communicate between one RIS and another RIS, which are at a distance greater than 100 kilometer, we can use satellite communication where this up conversion is mandatory. So during that time, we can use this RIS for up conversion. So these are all the different aspects of the metasurface where this frequency conversion is also possible. That is one application. So next one is this reflective dynamic metasurface for non-reciprocal beam steering and amplification. So beam steering, we have seen in the first two application. But what about this amplification? Like we have to do the wave manipulation such that there is going to be a constructive interference between two or more waves. So if there is any constructive interference, the wave will be amplified. So that is how the amplification is done. So you can see this violet rays. It is having huge amplitude because of the constructive interference. The manipulation should be done such that there is going to be constructive interference. And also, this metasurface is capable of operating in full duplex mode. You can see waves that is getting reflected from the board, and also the wave that is getting impinged on this board. So this metasurface is also capable of offering full duplex operation. And this was the first programmable metasurface that was proposed, that was written in that was present in the literature. The first paper we were discussing had a more clear picture. That's why I showed that first. So this was the case we discussed before. Like we'll be having the FPGA board in which we'll be giving different code sequences. So these code sequences will be mapped with one particular column of a metasurface. So depending on that, we'll be having different beams. The waves will be traveling along a particular direction depending upon the coding sequence. So that will result in different radiation patterns. So this is a programmable metasurface, and this is a meta atom we call it. That is, the size of this atom should be smaller than the wavelength. So and also this shape and the orientation of this atom is important, whereas the material property or the chemical constituent is not going to affect the wave manipulation. Either it is silver or copper, that is not going to matter. Only the orientation, the physical layout, and the interelemental spacing and size of the meta atom is going to affect the wave manipulation. So next one is there is another work in the literature which says that so if there is if this meta surface is, or the RAS that is having the meta surface is going to get connected with any moving entity like flight or satellite, there is no need such that the meta surface need to tilt. Instead, the meta surface can be attached with a gyroscope sensor, and the proper connection should be given such that the wave manipulation will be done such that it tracks the moving entity. So there is no necessary to tilt the meta surface, whereas the gyroscopic sensor will do that role. So this has also proven that the other sensors like humidity sensor or temperature sensor, other sensor can also be attached to this meta surface for relevant works. So next one is how the amplitude, see, this is a meta surface. We're attaching a FPGA board with it. And we'll be giving the sequences for different beams. We'll be giving the sequences along the column. We'll be giving the sequences along the column for beams in different direction. But how to alter the amplitude of different frequencies? So, see, you can see in the last graph, the different frequencies are of different amplitude. How to vary that? So to do that, instead of taking 1 bit per second, we can take 2 bits per second. So that has resulted in the different amplitude of different frequency components. So this is one of the paper which shows that we can use 2 bits per second to alter the amplitude of frequency of any electromagnetic wave. So next one is the clocking property, which we had discussed before. Say, for example, we have a detector here. We have a detector here, and that detector is and that detector is trying to detect this vehicle that is getting moved. But if you're attaching the meta surface here, we have a high possibility to hide this car that is getting moved, and detection is not possible. And so obvious that we should have other elements like velocity sensor and MC node and the computer and any arbitrary wave generation entities to support this application. But one of the possible application of this meta surface is clocking. That is, if anything should be hidden from any tracking element, we can use this meta surface as the clocking element. So next one is connecting this artificial neural network along with this meta materials. So what we can do now, we have the different, in the previous slide, we saw that all the codes, we have different set of codes, and each code is giving a different radiation beam pattern. So one possible application is like we can feed, we can feed some code patterns as the input, and we can train this neural network that is called a generative artificial neural network, such that whatever code is being given, this neural network will just predict the nature of the pattern that is going to be obtained after using the meta surface. So we have to first train and then test this neural network to predict what kind of pattern we'll get for the coding sequence we'll give. This is one of the work that is being present in the literature. So this was the setup that was given to, that is to verify the performance of this meta surface with this generative artificial neural network. So we have the meta surface here, and the deep learning system is being embedded in the processor that is being present here. So this is one of the applications of meta surface. And also we have this programmable meta surface. So we have a different coding matrix. That is, the coding matrix is nothing but the coding sequence that we will be giving either to turn on or turn off the elements that is present in a column. So depending on that, we can get either thin beams. We'll get thin beams if more number of elements are turned on nearby, because if more number of elements are turned on, the area of the elements that is operating will be larger. The physical area will be larger. The physical area is larger, the directivity will be very, very higher. that is one thing. And the coding matrix can be done such that where we can get a diffusion pattern also, depends upon the coding matrix. So next one is obtaining this orbital angular momentum. Uh, Orbital angular momentum is nothing, we can achieve that by changing the polarization. Either it is left-hand circular polarization or right-hand circular polarization. Depending on that, we can change the orbital angular momentum. So this is one application using this programmable metasurface. So again, we have this programmable metasurface. Depending on the input code, the FPGA will turn on and turn off the pin diodes, where we'll be getting different frequency signals of different amplitude. We have the same application here also, but the only difference is this is the time domain mode. It's not space-time domain mode. The previous case, we had the space-time domain mode, and this is time domain. One of the drawback in the space-time domain mode is the huge coupling between the different beams. To avoid that, we can completely go in this time domain metasurface, where we'll be giving one more information to the FPGA board in terms of phase. Previously, we gave only information to either turn off or turn on the pin diodes, but here we have to give some information regarding the phase also. So that's why this is called a time domain coding. So here we have the coding matrix, the time space coding matrix. So we have this XY space and time, and we have different entities here. And these entities are nothing but, these codes are nothing but they are highly dependent upon the reflection coefficient. So depending upon the reflection coefficient value, the wave reflection will mean the wave manipulation will be done. So reflection coefficient is nothing but they represent how good a wave is getting reflected. So these are nothing but the different reflection coefficient values. And again, it is not mandatory that this space-time coding should be a square matrix. Here the time entries can be less and space entries can be huge also. That is also possible. And we have this IOS assisted wireless network, that is intelligent omni-space assisted network, where we are having a star RIS hardware. Star RIS, STAR stands for simultaneous transmission and reflection to reflective intelligent surfaces. So basically we have an RIS here, and we have a data processor, so which is connected to an Ethernet switch that helps in routing. So we have a transmitter here. So basically this transmitter, whatever I'm sending, and we have USRPs also to RF transmission and reception. So basically I'm having a transmitter antenna here. So this transmitter antenna will be sending some input to this star RIS. So that star RIS will be transmitting the information that is received by this receiver antenna 2. This is capable of transmitting also from one end to the other end. And one more thing is this transmitter antenna, whatever it is sending, the star RIS will reflect it back also, and that is received by receiver antenna 1. So that is why it is called simultaneous transmission and simultaneous reception. And as usual, we have an FPGA board to control this metasurface. So that's why it's called simultaneous transmission and reception. And one more thing is, this picture just depicts the star RIS aided communication. So basically we have an RIS here, which is star RIS. So if from the base station there is any incident signal, and if the user, say for example, if this user A is not in the vicinity of base station and he is closer to this star RIS, he will be receiving the signal. And also this user C and user D, who are also very far away from this star RIS, are also capable of receiving the signals. This is nothing but a star RIS. It will reflect back and it also transmits. Both is possible here. And we have the pin diodes to manipulate the waveform. And next one is the simulation setup of the star RIS assisted NOMA. So in NOMA, we know that we'll be allocating power more to the users who are very far away because we have poor channel conditions, and the users who are nearby will be allocated with the less power. So one advantage of using this star RIS in NOMA is like if there are different cells, from the star RIS, you can get different frequency components, and that will avoid the intercell interference. So that is possible by using this star RIS. And also this secrecy, what they have proposed in this literature now to have more secrecy, they have added some artificial noise to have that secrecy. But coming to this RIS point, why they're using this RIS in NOMA? To avoid the interference, avoid the self-interference within a cell. So that is how this RIS assisted NOMA for a star RIS is proposed in this literature. So to conclude, the metasurfaces have become a revolutionary technologies, even that will be used in terahertz frequencies, and they are considered as the potential candidate for several practical solutions. And this metasurface can be used as a multifunctional metasurface by adding more active elements, and by connecting the metasurface with a field programmable gate array. This can be used as a programmable metasurface, and this programmable metasurface are the critical, or also can be a critical parameter to develop this intelligent metasurfaces, or this reconfigurable intelligent surfaces, which are the viable candidates for 5G, 6G, or beyond communications. Thank you. If there is any questions now, we can discuss.
Hello.
Yes, sir.
There are some shapes you have shown, madam, like a bean shape, some various shapes.
Yes, sir. Yes, sir.
They are original shapes of that materials, or it's an artificially prepared by us? That means the engineer.
No, sir. They are nothing but like just a normal material, sir, which are existing in nature. But the attribute is the material should have negative permittivity and negative permeability. So that is the thing. We have to alter the configuration of the material such that it is having this negative permittivity and permeability.
Okay, that's
So
the internal
basically, if you take
structure of that materials, right? That shapes are internal structure of the materials.
No, like they are normal materials like copper or aluminum or silver. They're normal materials, but using that material, we have to develop shapes like that, meta atoms like that. The shape of the meta atom should be such that it is offering negative permittivity or negative permittivity.
Okay. And how much phase it is going to change? Is there any predefined mathematical calculation? Suppose I want to shift the phase by some particular x angle. So is there any predefined calculations for that?
Basically, that we have this d pi by dx, like the orientation of the element now. Orientation of the element will help us to change the phase. We can check that in various simulators that we are using, sir.
Okay.
So, any other questions we have? Sir, I think there are not any questions.
Sir, you are muted.
I think if there is any question from participants, we can take that. I don't see any raised hand, but one can open the mic and speak. So Madhukar, if there is no question, maybe you can offer vote of thanks to ma'am.
I think Jawahar sir wants to say something.
Yeah, there are no questions, sir. There is no question.
Okay, so basically, I have one specific query for the ma'am. It was a
Yes, sir.
wonderful session on this meta surface of the basic concept you try to explain. So my request is
Thank you,
something
sir.
different. Uh,
Yes, sir.
that's some sort of like we have a e-learning platform. Government of India has a e-learning platform that we call
Yes, sir.
I got. So there is a very good session even for our service officers. So can you give permission to load the recording onto iGot platform of Government of India so that other stakeholders within the government can go through and take benefit of your session? So can we?
Definitely, sir.
Okay.
Definitely. Definitely.
Okay. So Madhukar would be writing a formal email to you. Maybe you can respond formally so that we'll
Sure.
keep that record and we'll try to use this for that. We also need your PDF so that we upload PDF also along with. Or if you have
I'll
any
share.
other resource or reading material on
Definitely, sir. I'll share them, sir. Definitely. Yeah.
it. Thank you. Thank you so much. So
Thank you.
Madhukar, over to you.
Yes, sir. So on behalf of FDP team and all the participants, I extend heartfelt gratitude to invaluable contribution of Dr. Yogeshwari to our faculty development program. Your session on Metasurface in wireless communication would be instrumental in broadening our understanding and application of this cutting-edge technology. Your dedication to share your expertise and insights have been truly inspiring, serving as a guiding light for researchers and practitioners alike in the field. Your presentation demonstrated a profound understanding of the subject matter, providing deep insight and a clear perspective that captivated the audience. Your expertise and eloquence were evident throughout and enriching our program significantly. We are immensely grateful to have such a distinguished speaker like Dr. Yogeshwari of Shastra University contributing to the success of our faculty development program. Special thanks are also due to all participants for their active engagement and valuable contributions, without which this session would not be successful. At the end, once again, I thank all of you. Warm regards and Jai Hind.
Thank you, sir. Thank you. Thank you.